Okay, so there is a binomial formula in your book, but I wouldn't look at it. I mean, because it uses certain variables, and they use k and k minus 1, and it's kind of a wordy definition. So to me, it's easier just to understand the process. So I'm going to give you 3 random problems, see if you can do it. So let's just say I gave you 3x squared minus y cubed, and I'm raising it to the 12th. Okay? And the question for you is, determine, I'll write it up here. Determine the 4th term in the expansion. Okay? And here's what I'm going to do. I'm going to give, and y'all hear this at home because I don't know if it's on the assignment sheet. I'm going to give you guys a quiz on Tuesday. Okay? Now I have put a practice quiz that's almost exactly like what you would see with just different numbers. And it's on there, and the key is on there. So, because normally what I do is I normally give them a quiz on a Monday, let's just say, but you guys won't be here, and everybody does okay or crappy, one or the other. And then they figure it out, and then I give them a second quiz on Tuesday, and I let them throw out the first one. But because that would take us 4 days or a whole week to do that, because you're never here, or rarely here, what I'm going to do is just put that practice one out there. So take it, look at the key, figure out what you've done wrong, and when you come back in here on Tuesday, that'll be the quiz that counts. Okay? And if you're still struggling with it, text me, email me, do something, and then we can talk about it. Okay, so determine the 4th term. So remember what you can do when you're determining these terms, rather than raise this to the 12th and actually expand it, which would have how many terms in it?
13.
13, right? Always one more than the power. And think about Pascal's triangle down to the 12th. You would be sitting there for days adding junk up. And then more than likely you make a careless error or whatever. So what I'm going to do is I'm going to use that little formula essentially, but I'm not going to actually look at the formula. And what 3 things can I always write down to get started? The 12 factorial. So I'm going to take that. That's 12 factorial. And that's always in the numerator of the fraction out front. And then what?
3x squared.
I'm going to copy down the 3x squared and the negative y cubed. Now when I was expanding them all the way out, I probably just said, oh, negative. I got alternating signs, and I probably wrote down just y cubed. But if I'm finding a certain term, I don't want to have to think through, okay, what the 4th term has what? Plus, minus, plus, minus. I'd rather not think through that. So I'm going to let the math do the work. Now, if I'm looking for the 4th term, then we say, some people call it the k value. The k value is this number that goes right here. But the k value is always what? If I'm looking for the 4th, this thing is always one less than that. So whatever place you're looking for, the value here, which some people refer to as the k value because they use k in the little formula, which I'm telling you not to look at, just subtract 1 from that and put that here. Make sure that you put these in order so that the 3 goes with the last term. Don't put the 3 here. All right, and then what do you know about these 2 exponents? They had to give me 12, so that must be a 9. And then whatever I put there with factorials, and you have set up what you need for this. And on your quiz, you'll see I'll probably give you 3 problems where I'll say set up what you would do. And then I'll give you 3 that kind of look like this and ask, or maybe a couple, and say simplify them, because I want to make sure that you know how to do the math. But I don't want to make it all about just factorials and multiplying. I want you to set it up for me and then show me you know how to simplify it. So if you were simplifying this, what would you do?
First you do the 12 over 9, and then it's 12 times 11 times 10.
Okay, so this number is going to be pretty ugly. 12, 11, 10, but all the 9, 8, 7, 6, 5, 4, 3, 2, 1 would have canceled, right? But you still have
3, 2, 1.
3, 2, 1, and I usually write just 3, 2 because the 1's not doing anything for me. And then I've got 3 to the 9th, which I didn't make you memorize that high, right? I made you go through 3 to the 8th. So 3 to the 9th is another times 3, but maybe I can get rid of that just by canceling that 3 out, and then it's something that I already know. And then I also have x to the what?
X to the x squared, so x to the 18.
So x to the square, x squared to the 9th is power to a power, so x to the 18th. I'm gonna put that at the end. And then what would 3 of these negative y cubes essentially give me? A negative cubed is a
Positive. Wait.
cube. 3 negatives would be a negative, right? So an even number of negatives here would have made it positive out front eventually. But an odd number of negatives, I'm just going to go ahead and take care of that negative and put it out front. I'm not going to write -1 cubed right here. I'm just going to bring the negative out to the front. And then finally, how many y's?
9.
9. So this is my problem. I'm just going to have to clean it up now. Now I can cancel maybe the 2 with the 12 and get a 6. But ultimately, I'm going to have to take out my calculator and multiply a 6 times 11, which is 66, not a calculator. A 3 to the 8th, which is a deep. Y'all studied it all.
Yes.
I thought about doing it today.
Wait. 65, 61.
Nice. Okay, so 65 to 61. And then you still have the 10, right? So there's a 66, there's a 65, 61, there's a 10. 10's easy to deal with. You just tack a 0 on the end. And then x 18, y 9. On your quiz, I try to avoid situations like this where I'm forcing you to go out to the side and multiply. I really do try to avoid that and make these numbers smaller. But whatever. Definitely multiply it out. A common mistake I see a lot of times is when people are doing this, this is what they do. They're multiplying all this out and they put the x to the 18th right here. And then they go, all right, -1 cubed is a -1 y to the 9th. And then they end up with a subtraction problem at the end. Are you with me? Don't do that. Oh, sorry, I forgot the negative here. Don't make it a subtraction problem. This is this times this times this. It's going to be one term. All right? Don't make it subtraction. In the end, it's going to be negative some big number, x to the 18th, y to the 9th. And I'll try to make it where the number's not that awful.
So you always just put the negative sign in front?
Yeah, because really I'm multiplying a bunch of junk together here, right? This is one single term. This is the 4th term in this expansion. So it's one number. It's never 2 numbers. So rather than mess around like this and confuse myself, if I immediately see that there's a -1 3 times and the problem is going to end up being negative, I just move it to the front and then I don't have to worry about it anymore. And it doesn't end up confusing me like this because it's sitting out there waiting on me. That would be my advice. All right, another way I could ask you to set this up, and I'm not going to work all of these. Another way I could set it up is say, determine the middle term. What if I gave you this same problem but said middle term? What did we learn yesterday?
12 over 12 factorial.
I can always start like that, but then what?
12 factorial over 6 factorial, 6 factorial.
Yeah, and I don't even have to think, do I?
And then 6.
Now again, if you're like, why does that work? I forgot. Well, if you remembered it, that it just does, you're fine. But why does it work is, remember, if there's a 12 there, then when you expand, there's 13 terms. So the middle one would be the 7th one, because you'd have 6 here on one side, 6 on the other side, then that 7th one in the middle. And if I'm looking for the 7th, that number's a 6, and then 6 and 6 adds to 12. But rather than overly think through it, and for those of you who are thinking, well, what would happen if it's odd? Well, is there a middle term?
No, it's like 2, but they're the inverse of each other. They're like.
There's a little bit of difference between them, definitely, but I'm never going to ask you that. Because if there's not a middle term, then I can't really ask you for a middle term when there's 2. So you would never see a middle term question, determine the middle term. You'd never see that on a problem that wasn't even. Are y'all with me on that? Okay, the last one we did not talk about, and this is a very common question, and it can get really a lot uglier than this, but it usually does at pre-cal level. But at Vestavia, they try to hurt everyone, so you never know there. But this is the kind of question. It says determine, so this is new, even if you were here yesterday in person, whatever, determine the constant term in the expansion And then they would give you something like, I don't know, 2x minus now what looks different about this?
X is on.
The X is on the bottom.
Okay, so you have x's in the denominator, and also you don't have x's and y's or a's and b's. I have the same variable. All right? By the way, what's a constant term mean? You know this. Don't be shy.
Actually,
Okay, in math, right, you've got numbers and you've got letters. And the letters are called
constant, or the variable.
variables. And they're called variables because they vary. So the numbers are the constants. Now, if it's a number in front of a variable, we call it a coefficient. Okay, but if it's just a number sitting there by itself with no variable, it's not changing, right? Okay, I mean, unless it's, well, even my age is varying. But like if I have $5 and I put it on, it's not changing at all, it's just $5, right? So constants are numbers that don't have variables. Now, in the problems that we've done so far, the expansions, we've always had two different variables, haven't we?
Mm-hmm.
And as one is going down, what's the other one doing? Going up. So there never was a term that didn't have a variable in it, right? Even when I had like no y's, I had tons of x's. Or when I had tons of y's, I had no x's. I still had a variable. Well, in this one you can think about, I'm going to be starting with x to the 4th to the 9th over here, right? And it's going to be decreasing in value. And over here I'm going to be starting with x squared on the bottom to the 9th, which is a ton of x's on the bottom. And it's going to be decreasing. Isn't there a chance, maybe, that as this one's going down on the top in value and this one's going down on the bottom, that at some point in the middle, all the x's cancel? Does that make sense? You're going to see it in a second. I just don't want to write out all 10 terms of this. But now watch. You don't even have to overly think too much. Because anytime I'm asking for a certain term, what can you always do from the beginning? 9 factorial over something, and then you can write 2x to the 4th negative 3x squared. The only difference here, we don't know what term it is. And if I don't know what term, I don't know what to just put right here, do I? But let's just be creative. A constant term is when all the x's cancel. Can you think of numbers that go here and here that would give me the same number of x's in the numerator and the same number of x's in the denominator so that all the x's would cancel? And then also keep in mind that what do these two numbers have to add to? 9. So listen, I'm going to be like a moron and just totally guess terribly, okay? Maybe it's 0 and 9. Now, if I did 0 and 9, you can clearly see that I have nothing in the numerator here. It's just 1, but I would have 18 x's down here, wouldn't I?
Yeah.
And then other numbers. But there's no way all the x's cancel, do they? Well, then there's no way that works. What about 8 and 1? Now, if I have 8 and 1, this would give me a 2x to the 4th, so there are x's up top, and this would give me what? 3 to the 8th, x squared to the 8th, which would be x to the 16th, and 8 negatives would become a positive. But right here, would all the x's cancel? They wouldn't, would they? So I would not have a constant term. But you kind of see where I'm going, right?
Yeah.
And then if I'm just going to jump to, well, I'll do 7. If I did 7 and 2, and again, they have to add the 9, then I would square this, which would give me 4x to the 8th. And then here I'd have 3 to the 7th, which is,
So 2187.
but it would be positive or negative. It would be negative, so I would probably just throw the negative out front, and I would have x to the 14th. Now I'm getting closer, right? The numbers here are getting smaller, and the numbers here are getting bigger, but they still don't all cancel. But at some point, what happens? And at this point, I have 2 to the cube, which is 8x to the 12th. Here I have 6 negatives, which is positive, and 3 to the 6th, which is
729.
729, and x to the 12th on the bottom. And at this point, you go, oh, all the x's cancel. Now, hopefully you don't have to draw it out as long as I just did, right? But once you see them cancel, you can go, oh, well, now I can complete the problem. Because if I have a 3 and a 6 here, what else has to happen? 3 and a 6 here. So basically, you just guessed and checked and revised it. And I'll give you a little hint. If you have more x's in the numerator than you do in the denominator to start, then you're going to have a smaller power there and a bigger power there. So that's kind of where I start my guessing. That makes sense, right? Because they're going to have to balance it to equal. And then right here, I can clean this up. 9, 8, 7 over 3, 2. And yeah, I might be able to cancel some of this junk out. So I end up with 12 times 7, which is what, 84, times an 8, times a 729. And I'm going to have to figure out what that is. It's definitely positive, because you remember, 6 negatives is a positive. But all my x's are gone. So I would end up with just a constant term. Y'all seeing that? Okay, that's what your quiz is about. And there's a couple other things I want to point out. Gosh, it was the very first math team I ever had. Y'all may know this guy. His name was Will. Dang it. How did I forget his name? Will's not going to help you because he's Mr. to you. He's like 40 with kids. He lives in Homewood. It's been a while. Anyway, this guy went to math tournament, he came back, and I was like, guys, listen, I have no idea how to do this. And he's like, well, I got it. I'm like, what'd you do? He goes, like, well, this is the problem. It said determine, basically it says, if you expanded this number, that would be really ugly. How about this? The question was, if you took this, no, it was bigger than that. Here, how about, something like that. It said, if you took this number and expanded it all the way out, and then added together all the coefficients and all the constants, what would you end up having? Except that probably the number was bigger there. But anyway, it would have been impossible to take the time, not impossible, but it would have been really tedious to write this out 5 times, right? And he goes, well, all I did was take the 2 and subtract the 3 and add the 3 and add the 2, and I just raised that to the 5th. And if you do that, you end up getting 4 to the 5th, which you guys know is same as 2 to the 10th.
1024.
Nice. Okay. And I went, well, that doesn't work, man. You just got lucky. Well, dang it. Anyway, so I went home that night and I started writing out polynomials and multiplying them out. It took me forever. Just started seeing it. I'm like, it does work. So we called it Will's Rule. It's still in my summer reading, which you guys didn't get, but you'd get it next year if you're around for my class. But we call it Will's Rule, and we still use it. But later on, I started seeing that there are patterns like that that you can apply. And you see the first one with Pascal's triangle. And this is a very common question that you would see. Maybe not common, but in the history of math team that I've been around, I've seen it a ton. They'll say something like, determine the sum of the terms in the 10th row of Pascal's triangle. Well, a sucker does this. Man, I can do this. I got some free time, right? And they go, all right, 1, 2, 1. And they start writing. And hopefully and you can see I'm slowing down, right? A little bit. And they're like, oh. And they're starting to lose steam, but they're like, hey, I got nothing else better to do. And they keep going, right? And the problem is, even if they get this 10th row, oh, by the way, the 10th row isn't really the one with the 10. The 10th row, this is the first row, second row, right? First, second, the third, this is the fourth, right? But the fourth row is the one that came from the cube. And this is what can be really confusing at math tournaments. If they say 10th row, if you look in your book, they don't call the 10th row, they don't call it the 10th row, they call it the 9 row. 10th row is the same thing as the 9 row. And they call it the 9 row because it was created from A plus B to the 9th. So the 7th row isn't really the one with the 7, is it? The 7th row, first, second, third, fourth, fifth, sixth, seventh, that's the same thing as the 6th row. So the 6th row is the 7th row. And that can be confusing because they word it differently depending on which school you go to or what they feel. So on my quiz, I'm going to ask you one or the other. If I say the 10 row, then I need you to add up all the terms that are actually in the row that has the 10 in it. But if I say the 10th row, I mean for you to add up all these terms. Well, I hope you don't do any of that, because this is going to take a while to add up all that junk. You might have already gotten there. But notice this pattern. If you add up all these terms, I'm sorry if y'all can't see this, but you know it's Pascal's triangle. That is the same thing as 2 to the 0. 2 to the 0 is 1. That's the same thing as 2 to the first. The sum there is 4, 2 squared. The sum there is 8, 2 cubed. The sum there is 16, 2 to the fourth. And if you refer back to what we did here, if you think about it, A plus B to like the 4th power, what are the sum of the terms in the expansion? 1, 4, 6, 4, 1, but isn't that 1 plus 1 to the 4th? But you can not only extend it with binomials, you can extend it to anything. You just have to be careful. So to answer this question, determine the sum of the terms in the 10th row, you have to go, oh, the 10th row is the one that had the 9 in it. The 9's in it. And that came from A plus B to the 9th. So 1 plus 1 to the 9th, 2 to the 9th. And we know that 2 to the 9th is nice, 512. Right? Yes? Just be careful. If I say any of the whatever, you got to subtract 1 from it. Go 2 to that power. If I give you the 9 row, 8 row, 7 row, then just go 2 to that power. Are y'all with me? Okay. So know this little trick, and then also know this. If I want the sum of all the coefficients and the constants, just like it works for A plus B, or 2 to that power, it also works this. You just have to add all of them together. And then raise it to the power. Y'all with me? Any other questions on this kind of stuff? All right, so here's what we're going to, y'all feel like the math just make you quiet?
Yep.
Is there anybody in here who's like normally really outgoing and it's like it's you're just stifled? You know?
No.
Because it's brutal. Like I thrive. I know it's already a small class. But like I'm kind of like I may have used this analogy before, but I'm more like a leech. I think I did, yeah. Yeah, because I was talking about McBride. He can just stand up there and be funny. I need some help. Y'all might have to get like a little plastic shield so I can see your faces.
Yeah, I
your
feel
mouth.
like it's kind of, especially if people are talking quiet, you can't like read their lips. So
And I need that. Like as you get older, your ears start going too. Like I'm really locked in, but anyway, trying to help a brother out. All right, we're going to jump into some matrices. Remember I told you I was just going to throw this out. Normally I do it because it's such a common question at a tournament. It usually really helps us out in the early parts of the year. And also matrices I put out there because determinants, which we'll do in a couple days, also are very common and prevalent. But the only reason I'm not just saying, oh, we're not going to math tournaments, I'll just do them at the end of the year, because you'll see we're on chapter 11 and chapter 16. It's because I've already made all my 9 weeks tests up and all my exams up, and I don't want to redo everything. I have no time as it is to do much of anything with all the new junk they've tossed on me. So anyway, let's take a look at matrices. And if you do have questions on any of this other stuff, just let me know. And remember, your quiz will be when you get here on Tuesday. I'll give you a quiz, so don't be surprised by it, but there is a practice one for you. If you can do that, it will be really no different. It'll really almost look the same. Okay? So maybe don't even look at the key. Maybe take it and then look at it and go, holy crud, I don't know how to do this or that, and send me an email or something if you need help. Okay, so matrices has nothing to do with the movie. If you've watched the Matrix first one or the whole series or whatever, a matrix is a way to just organize information. Okay, now we're not going to get it, like if you use Excel spreadsheets are basically matrices. All right, like I can take something from this element and add it to another, and I can use formulas and everything to do those calculations. Accountants use it all the time. There are a lot of applications you can use with matrices, whether it's creating codes. There's a class in college I took called coding theory, which was all about binary codes and how they structure binary codes to keep computers from making mistakes. And they'll just extend these codes, and if because computers make mistakes. There are errors that they make, but if they have enough little proofs built into them, those errors can be caught and minimized. And because we have such huge, powerful computers now, you don't even see that. It just doesn't show up like maybe it did in the 80s and 90s. But anyway, what we're going to do with matrices is not really look at the application, but really more just the math of it. Okay, and that may seem a little boring, but we are going to learn enough this year so when we get into pre-cal, we can start actually solving systems with our calculators, because our calculators have some great programs that can actually solve these systems using matrices and other processes. So we're going to dabble in it this year and learn just all the basic stuff, and then we're going to get a little dirtier next year if you are around. Okay? And actually, like I have many students that will come to me in engineering at Auburn or Alabama and say, yeah, I took a coding class. I learned nothing new more than what you taught me, and which is shocking that they could do that for a semester, but literally nothing new. It was the exact same material, just regurgitated and much more slowly. So we will do a lot in here this year and next year with it. And I think they're pretty helpful, but it's going to seem a little dull starting out. So I'm going to just throw out the basics to you. I do have an assignment sheet that I can give you. You've probably been looking at the one online, but this is a hard copy. All right. So, a matrix. A matrix is basically and that's matrix, the plural would be matrices, and it is a rectangular array of numbers. That's basically a simple definition. And when I say rectangle, a square is a special kind of rectangle. So it could look rectangular, square, whatever. So it could be something like this, and you put brackets around it. It could be something like that. It could be something like this, whatever. It could be a these are just random matrices. Now there are dimensions of matrices, which are like the size of them, and we write the size kind of like you would with wood. Like with wood, you can buy a 2x4 or a 2x6 or 1x4 or 1x8. So this right here, the way you talk about the dimensions of a matrix, the dimensions, we always list the rows, and then we put an X, and we put the number of columns. Now sometimes people get rows and columns confused, because like on this, I might call that a row, or this a row, or this a row. But which kind of seems like the up and down part. I know we're flat here, but this right here is a column, right? Kind of like a column on a house, goes vertically. And then these are rows. So if I'm counting them, how many rows does this thing have?
But
3 rows and 1 column. So I would say that the dimensions of this is a 3 by 1 matrix. This 2 by 2, this 2 by 3. And it's important for you to understand those dimensions because when we get to matrix multiplication, which is probably Monday, you can only multiply certain sized matrices together. Like you think, oh, I can multiply a 2 by 2 by a 2 by 2. That's true, but I can't multiply a 2 by 3 by a 2 by 3. But I could multiply a 2 by 3 by a 3 by 8. So there's all kinds of weird things that we'll talk about later, but it is important that you understand the dimensions because if you get that backwards, then when you run your little check to see if you can actually multiply them, you'll be checking it wrongly and you'll go, oh, I can't multiply this when you really can. And then you're out 5 points on your test or whatever. Okay? Also, there is something called the zero matrix. A zero matrix is kind of obvious. It's just a matrix that has nothing but zeros in it. And that's kind of important because kind of like the 0 is the identity element with addition. So if you multiply by 0, if you add a 0, you get itself. That's true with the matrix. If you add a 0 matrix to another matrix, assuming you're able to add it at all, if you can add it, then you would get the original matrix. So it doesn't really do anything. And a lot of people take a shortcut in writing that. They just go, hey, the 0, 2 by 3. Just so they don't have to write so many zeros. Okay? And it's possible, I guess, to have a 1 by 1 matrix. A 1 by 1 matrix, like if I had that, I could argue that it's a 1 by 1. But most of the time, if you don't need a rectangular array to organize these numbers, then we call that a scalar number. So you're not going to really see that. Numbers that aren't in a matrix, like maybe a number that's on the outside of a matrix, something like that, we call numbers like that or like that. We call those scalar numbers. Scalars, S-C-A-L-A-R. Your age is a scalar. Your height is a scalar. Those are just random numbers out there. We don't call them scalar numbers typically, but with a matrix we want to determine or maybe acknowledge that it's different than the stuff that's in there. So a number that's not in a matrix we call a scalar. And we'll talk about how to multiply a scalar times a matrix and things like that as well. Okay, another really important one is the identity. The identity matrix, which we're going to use when we get to multiplication. Okay, let me get rid of some of this. The identity element is kind of like the identity matrix. Do you remember the identity element for multiplication? What was the identity element in multiplication? The thing you could multiply by and nothing changed. 1. Well, there's an identity element here, but the matrix that gives you the original matrix when you multiply by it depends on the size, but it could be a simple scalar like we do in regular life, multiply by 1. But if it becomes bigger than that, they're always square. Right? They're not rectangular. They're always 2 by 2s or 3 by 3s or 4 by 4s. So you're probably not going to see that 1 by 1. But they're not just a bunch of 1s. It's 1s along this diagonal and 0s everywhere else. So if it's a 2 by 2, it would look like that. If it's a 3 by 3, it would look like this, and etc., etc. But it's always that diagonal going from top left to bottom right. And when we multiply, you'll see why that happens. Once you learn the way we multiply, you'll go, oh, that makes sense. A couple other things that I don't think are going to be a big deal, but in order for one matrix to equal another matrix, if they're equal, they have to be the same size. Like I could not say, hey, determine X. Because this doesn't make any sense, okay? These aren't equal because they're not the same size. But if they were the same size, then it would be pretty easy to see if these are equal. What would X have to be? 2, and Y would have to be 3, but you'd have to have corresponding elements, which makes sense, right? And if I have one thing equal to another thing, everything has to be the same. in order for them to be equal. So at some point, you'd have to be able to match up these terms right here. So you gotta have the same dimensions. They'd have to both be 2x2s or both be 3x4s or whatever in order for them to be equal. Now that's something that I think is kind of obvious, but adding is a little obvious as well, but it makes you think it works for everything like multiplication and things like that, but not necessarily. So let's just talk about addition of matrices. So to add them, you have to also have the same dimensions, and I do. I've got a couple of 2x3s here. And what would be your guess as to what size I end up with? Throw out a guess. Same size? That's true with addition. It actually is not necessarily true with multiplication, but we won't do any of that tonight. So what do you think you do to add these?
Just add on. I like the same addition name.
That's right, we call those corresponding elements. So if this is in the same, like if this is in the first row and the first column, then I would add that to the term that's in the first row and the first column. So good, you're just basically matching up these terms and adding them or doing whatever it says to do. So you would end up with a 7, 1, 4, 8, -1, 1. Don't you love the way these colors go together? Are you with me?
Yeah.
So that would just be addition. I rarely see anybody make a mistake with this unless they're just careless and go, -3 + 4 is -12 or something like that. But just be careful, okay? Now, the way I can make this uglier is to start throwing scalars in there. And remember, a scalar is just a number that's what? On the outside or not in a matrix. So if I throw a scalar in there like 2 times, and then I give you, what would you do with a 2? Or let's make it interesting. What would you do with a -2? What do you think happens here? Take a guess. It's kind of like this distributive property. It's going to go into every single term. So that -2, if it's a scalar, goes into every single term. Now, you don't really think about it initially until you start doing this, but there's 6 ways I can make a mistake here. You got to slow down and really think about this, because every time you make a mistake, you get dotted. And there are problems that you'll have 18 calculations to make. And if you go 17 out of 18 and miss one little calculation, you're still getting dotted and you're losing a fourth of your credit. So slow down on the math. -2, -6, -10, +2, 0, -8. And then sometimes you'll get this, and then maybe I'm subtracting from another term. It's like, so you do the first part, what are you going to do with the second part?
Distribute the 5 and then subtract.
Okay, now that's one option, and it's totally fine, but let me just tell you, people that do that tend to make a little more, a few more errors statistically than people that multiply the whole -5 in there and then just change this to a plus. Let me just show you why. It's just one other thing your brain has to think through. Let's just say you just chose to put the 5 in there. You would have gotten 10. If you had done it this way and not multiplied, left the negative there, you're going to end up with this, right? Are you with me? Because the negative's still out there. But now I have to do things like -6 minus a -30. That's a lot of negatives floating around in your brain. Now you may go, it's not that big of a deal. That's great then if it's not. But I'm telling you, in the history of me grading these tests, which I've done a long time, the people that make more mistakes tend to do this. But if you take that negative and just bring the whole thing in, then you get -10, +30, -35, 0, +5, -20. People tend to do a whole lot better with, oh, -6 and 30. It's just one less thing their brain has to think about. So that would be my encouragement. But whatever you do, don't multiply the negative in and turn that into multiplication. Because if you do, this actually doesn't multiply. And you'll learn why on Monday. Okay? So right here, what do I do now? Negative 2, negative 10. Negative 6 and 30. Negative 10, negative 35. 2 and 0. 0 and 5. Love the 0. Negative 8, negative 20. And if you think about it, you just did 6 calculations there, another 6 right there, another 6 adding them. That's 18 different ways you can go wrong. And every time you make a careless mistake, you get dotted, for the most part. So really slow down and be careful. Y'all with me? All right. The only other thing I have, well, actually I have time for a little bit. What if I did this? What if I said solve for x? And I don't know why the book uses capital big X, but they do a lot. So what if I gave you this? 2x plus, I guess it doesn't matter, but I'll put it up here. Now, I want you to think for a second. They're asking you to multiply 2 times something and add it to this matrix. Does that tell you anything about what x is then? If I'm adding to, I'm not the actual value of it, but if I'm going to add it to a matrix, what does it have to be?
Matrix.
Another matrix. And more specifically, if I'm going to add this to a 2 by 2 matrix and end up with a 2 by 2 matrix, what must x be?
2 by 2.
A 2 by 2 matrix. So this x right here just stands for a big 2 by 2 matrix. So in our answer, when we're finished, we're actually going to have a 2 by 2 matrix that this is equal to. In some books, they write this, but this one does not. Or maybe they do in a couple problems. In some, they would do something like this and put A, B, C, D. So you would recognize that, oh, I'm finding out what that 2 by 2 matrix is. And you're figuring that out. You'd be solving for the A and the B or whatever. But our book just puts an X. So let's think about that. Using what you know about algebra, what do you think you ought to do to get this X by itself?
Divide
Divide everything by 2.
Okay, you could right now, but is that really what you do?
Or
If I gave you this?
Subtract it first.
Yeah, if I gave you that, would you be dividing by 2?
No.
You'd be getting that 3 over there, right? So why don't we just do that? Why don't we take this and subtract this from both sides? And if I subtract this from both sides, it's going to be gone there, leaving me just this. But what would happen? I'm going to end up subtracting the 2, 1, 3, 2 here, and subtract the 2, 1, 3, 2 there. And that cancels. Now, what do I end up with? Now, because this is not a whole lot of negatives, I'm probably just going to go 3 minus 2. But if it bothered me enough, I could take this negative and do what? Make it positive and multiply it in. So if you want to do that, and that helps you, great. So what do I end up with when I when I add these two together?
1, negative 3.
1, negative 3,
Negative 1.
1, negative 1. Now what do you think you're going to do?
Divide it by 2.
You're going to divide by 2. Now I will say this, with matrices, we don't do a lot of division. But what's the same thing as dividing by a number?
Subtracting multiple times.
It can be thought that way, yes. Especially when it comes to trying to get a remainder. But no, hold on. What do you do to divide by something? You multiply by its, well, multiplicative inverse, or its reciprocal, right? So to divide by a 2, I'm going to multiply by a half, right?
Yeah.
And you'll know why I'm talking about. We cannot actually divide by a matrix. So I love to, on the matrix section, just say, let's not divide at all. And there's a way you can actually get rid of a matrix that you want to divide out, even though you can't divide. And we're using inverses, actually. It's like a multiplicative inverse, but it's a really weird way to do it, which we'll talk about later. So once I do that, I get my x by itself, which is my goal, and I end up with half of all this, which is half, negative 3 halves, half, negative half. And again, what did we say x was again? Some 2 by 2 matrix. So if I took that, plugged it back in here, doubled it, and added to this, I should get that original stuff on the side. Okay, we got 4 minutes. Let me give you the ugliest thing you might see tonight. We'll just go with it here. How about this? 1/2. Let's do this. 1/2 x minus 2 brackets 3 negative 1 4 2 equals 4 bracket 5 2 negative 6 1. What would you do first here?
Distribute each.
The negative 2 and the 4 in? Why not? In fact, if you look ahead a little bit, what are you going to end up doing with this term right here?
Adding it to the.
You're going to add it to the side? So why don't we just leave the negative there then? You all tracking with me? If I just bring the 2 in, you don't have to. Then you get 6, negative 2, 8, 4. Over here you get 28, negative 24, 4. If I do that and leave it negative here, then when I add it to the other side, I won't have that negative bothering me, will I? So I'm going to move all of this over, or add it to both sides. And that way I don't have a negative and it's nice and clean, ready to go. Hopefully that is in my video. Sorry, I'm moving it over here and it's a plus if you can't see that. So I get 1/2 x, and what do I get when I add these two together?
26.
Negative 16/8. And then now what would you do to get x by itself? Multiply by 2. Canceling the 1/2. And what, 52, 12, negative 32, 16. And that's probably one of the hardest things you'll see. Hopefully not a big deal. Y'all with me? All right, got a homework assignment on that. Remember to look at that quiz for your own sake. Your quiz won't be till Tuesday, so I guess you can wait till Monday night on it. But if you're at home, then your quiz. If you're a virtual, then you're not going to have a quiz. So make sure you practice that one, so that you'll be ready for your test. All right, good times.